Okay, as I said, today I am moving forward with rainfall runoff modeling. We are close to the closure of this topic. It will be closed on Monday. And we already introduced two models. You know them. Hopefully you understood how they work. And today I am introducing another class of models. And it's a transition between the two simple, let's say, very schematic models, very conceptual models that we used so far. I will make a transition to a more complicated class of models. And the transition will be, in my intention, smooth. But nevertheless, I perfectly realize that given that I am moving to a more complicated class of models, I perfectly understand that today it's a lecture that is not easy to attend and to follow. So I would like that it's more than a lecture, it's a discussion between us. If you don't understand, just stop me. And it's also a problem when I teach in Italian this class of models, and in English, of course, it's more problematic because my vocabulary is not so extended. But I think it will be nice. So let me try to move forward, starting from what we did. So basically, we closed the past lecture with the linear reservoir, and the linear reservoir was schematized in this way with a flow of precipitation per unit time over the catchment entering the reservoir. In the reservoir, you have water content, which we indicated with the symbol WT, and then an outflow, which we indicated with the symbol QT. And then you know that we wrote the continuity equation in this way: PT minus QT is equal to K the Q. Let me see, K, let me write this way, the WT into T. And then we said that WT is equal to K, which multiplies QT. And then we combine these two equations, and then we obtained an explicit expression for Q. Now, let me say, first of all, as I anticipated last time, that you can also integrate numerically this equation. So given these two equations, even without combining them, by keeping them separated like they are now, you can integrate them numerically. And to integrate them numerically, you just have to turn from the infinitesimal increments to finite differences. So let me just rewrite this equation by using finite differences. Just this one. And it's very simple. You refer now to instant t like before, and then you say pt minus qt is equal to delta wt over delta t. Now you refer to a finite increment of time. And usually, given that precipitation and river flow are observed at a given time step, you use as delta t the time step to which observations are taken. So basically, if you have hourly rainfall, then you fix delta t to 1 hour or 3600 seconds, which is the same thing. And what you do basically is you start from time 0, and then you get rainfall, the flow of rainfall over the catchment in the first hour. And then what you do is to compute the delta W in the first hour. And of course, given that at the beginning of the first hour the reservoir is empty, you assume that the outflow is 0, because you see here, if W, sorry, I forgot a T, an index T here. If W is 0, the outflow is 0. Okay? So basically, you compute delta WT has Pt times delta T. And let me say that this is 1, not T, because let me be more explicit. So this is 1 at the end of the first hour. You have delta W1 equal to P in the first hour times delta T. Now you may say, look, I don't agree that the outflow is 0, because in the first hour, during the first hour, while it's raining, the tank is getting some storage. So it means that after a couple of seconds, as soon as you get some storage, water storage in the tank, you start having also some outflow. So you may say that. So you may say your assumption of outflow, null outflow in the first hour is not, strictly speaking, verified. Okay, this is the numerical approximation. Basically, when you turn to infinitesimal increments to finite differences, you have to assume that the variable during the delta t that you took are constant, which is not true. Okay? This is the problem, not the problem, this is the numerical approximation. It's not a problem to take the variable constant when the time increment is infinitesimal, because of course it's infinitesimal, so you can assume that the variable is constant for an infinitesimal time step. But when you turn to a time step of 1 hour, of course, the assumption of constant variables is not met, is not reliable, and induces an approximation. This is what we call numerical approximation. It's important to be aware of that. What is in practice the effect of the numerical approximation, what induces the numerical approximation, and what is the practical effect. The practical effect is that in this case I assume Q equal to 0, which is not true. Of course, this assumption is as more reliable as your time step decreases. If you take a time step of 1 second, this is fine for hydrology. If you take a time step of 1 month, you can't assume that for 1 month you don't have any outflow from a catchment. Of course. You have to be aware of this effect of the numerical approximation. Okay, then you may say, okay, let's take for true that we can't avoid the numerical approximation, but you may say your assumption could be improved. Your assumption of 0 outflow, you may say it could be improved. Because you may say, once that you got an estimate of W according to this equation, okay, at the end of the first hour you get an estimate of W, which is not really a good estimate, because W will be lower than what you estimated. Why lower? Because during the first hour you have some outflow from the tank. So W that you estimated in this way, I estimated in this way, actually is overestimated. So you may say, once that you got this estimate, then you may say you could compute a Q1 according to this equation. So you may say, okay, given that delta W is this, and therefore given that W1 is equal to W0 plus delta W1, I get an estimate of W1, and then I can get an estimate of Q1, which is W1, sorry, let me use the subscript, equal to W1 divided by K. That's true, I can get this estimate. And then, what I could do is go back here, not here, sorry, here. Go back here and recompute this delta W1. I could recompute it in this way. Delta W1. Okay, you may notice an inconsistency. Sometimes I used 1 between parentheses and sometimes as a subscript. So let me change this, okay? So I could recompute delta W1 as equal to P1 delta T minus Q1 delta T. You may say this, you may say you can improve. But I could improve even more because even this W1 is not correct. Now it's overestimated. This delta W1, now it's overestimated. It's overestimated because I assumed that for the whole first hour I have an outflow which is the maximum one that I have at the end of the first hour. So I could again perform another iteration. You see that this is an iterative procedure. But indeed, if you perform many iterations, you converge to a solution that is close to the correct one.
Sorry, it is an underestimation.
Now it's an underestimation.
Okay.
If you think to it, it's an underestimation now at this stage. Because you overestimated Q1. It's overestimated why? Look at how Q1 was computed. It was computed by using an overestimation of W, and therefore it's overestimated Q1. Okay, now let me summarize this reasoning by saying that I introduced two methods of numerical integration. One is simple, and the other one is more complicated because it needs an iteration. So the first method that I used, it's a method that assumes that each variable in each time step takes a constant value, fine, which is equal to the value that is assumed at the beginning of the interval. Basically, what I did in my first method is to assume that the outflow was 0. Why that? Because at the beginning of the interval, the outflow is 0. So, if I assume that, I repeat, in each time step, the variable are constant, fine, and take a value that is equal to the value at the beginning of the interval, it's one thing. And it's called, this method of numerical integration, it's called Euler method. In Italian, metodo di Eulero, which is the simplest method that you may use for numerical integration. But of course, it has some approximation. The second one was an iterative method, and it's called the Runge-Kutta method. Or probably Runge. I'm not sure how the pronunciation is. I'm not a mathematician, sorry. And the Runge-Kutta could be of order 1 if you perform only one iteration, order 2, order 3, order 4, depending on the number of iterations that you perform. Let's say that with the modern availability of computing resources, it's better to avoid very significant numerical errors. And therefore, you know, the Euler method it's not really the best. We will use it because it's simpler, but it's not much more complicated to introduce an iteration. And of course your question could be, how could I judge if the approximation is fine? There is a very simple method. When you finish your simulation, and even for subset of your simulation, subtemporal sets, after 10 hours, after 20 hours, just compute a mass balance from the beginning of the event. Take the sum of the rainfall, take the sum of the outflow, and take the storage. And try to see if the continuity equation is satisfied. It will be not, because of the numerical approximation. Of course, this continuity equation is satisfied if these variables are estimated correctly. PT is given, but QT and the storage, if they are estimated correctly, you get an equation that is satisfied after 10 hours. But if you make a mistake in the estimation of QT and W, then it means that after 10 hours, if you try to check the mass balance of the reservoir, you get an error. So a typical rule of thumb in hydrology, in this kind of models, is that if you get an error in the mass balance of 5%, it's fine. If you get an error that is more than 10%, it depends on the time step that you are using. It depends also on the behavior of the event, because if you have a rainfall that is fairly constant during your simulation, then you know you don't get very. Do you remember with constant rainfall how the hydrography is? It tends to a stable situation. In a stable situation, even if the numerical approximation is fine, because in a stable situation you don't have the variables that are varying much within the time step. You have problems in numerical approximation if during the time step the variables vary a lot. So it depends on the behavior of the event, on the extension of your time step. So you may try the Euler method, and then at the end of the simulation try to check the mass balance. If you see that it's, the error is between lower than 5% or let's say between 5 and 10, you can still accept. Why that? Because I told you that in hydrology the observations have an error that usually is about is from 10 to 25%. So if you get an error in the simulation that is 10%, it can be accepted. Otherwise, it's better if you change your numerical integration scheme. And there is another problem which I'm not expecting, but I want to mention to you, and I'm sure that you already dealt with numerical integration in some other subjects. There is another problem which is stability, because one problem is the error that you make while the variables are still stable. There are some errors that amplifies time step by time step and lead to, for instance, outflow that tends to infinity. This is not the case. In this case, you will never get outflow that tends to infinity. But in some cases, in hydrology with other models, you may have some instability. And then you clearly see that your simulation at a certain point becomes clearly unreliable. Or one other problem that you may get in this case, and if you make some experiments, you will see that you may get some up and down in the outflow. If you think of the situation that you get here, it's logical that you get some up and down, because in the first time step you underestimate Q. In the second time step, you have overestimated the storage in the first time step. So in the second time step, you overestimate Q. Because if in the first time step you put Q equal to 0, at the end of the first hour you get too much water into the reservoir, which means too much outflow in the second hour. So you may get the storage in the reservoir that goes up and down, and also the river flow up and down, and which is not physically reliable. So you see also these problems. For the particular case of variables that, let's say, explode, tends to infinity, there is a full theory of that deals with numerical stability. One thing is numerical approximation, the other thing is numerical stability. Depending on the type of model that you have, depending on the differential equations from which you start, there is a full theory that deals with stability. We are not dealing with it. If you took some subject of hydraulics or fluid mechanics in your career and you dealt with the Dessin-Venant equation for open channel flow, and you dealt with the numerical integration of the Dessin-Venant equation, you got familiar with the courant condition, with the courant number. These are conditions that have to be satisfied, basically conditions on the time step, shouldn't be too large, have to be satisfied to avoid instability. I'm not dealing with this subject, and also because in this case, you know, these equations, the kind of instability that they present is just limited to oscillations, not to explosion. Anyway, the moral of the story is that we have the means to solve these equations numerically. And let me say that in most of the practical cases it is convenient to do that instead of integrating, because you know we are working at a finite time step, and therefore even the integration is a numerical integration, is not an analytical integration. So in many cases it is convenient to work with this numerical scheme which I introduced. And you may ask me, please give us more details when it is convenient, because of course it's also easy to apply at the PC the integral by transforming the integral in a summation. So you may ask me when it is convenient. And I would say that in this case you have a very simple situation where the equation can be integrated analytically. So in this case I would say when you have an integral which is expressed nicely in an analytical way, it's better to use the integral form, and then you perform the numerical integration on the integral form, which is not really a numerical integration, it's a numerical computation of the integral. And instead, if you can't analytically integrate the differential equations from which you start from, then it's better to put them at the finite difference form. Because the linear reservoir model, it can be integrated because it's very simple and because we assumed a linear relationship between the outflow and the storage. If you put here a quadratic relationship, you are already stopped. You can't integrate it. This is why a linear relationship is used. And this consideration gives to me the opportunity to move forward and tell you, if you want here to use a quadratic relationship, because basically the relationship between storage and outflow is not linear. If you want to use a relationship that is different from linear, that's fine, no problem. And in particular, let me say if it is quadratic or it's, yeah, it's the square should be put here. Yes, here. So it's the square of the outflow that depends from the storage, strictly speaking, if you want to adopt a physically based representation. Basically, the outflow depends on the square root of the storage. It's not a linear dependence. So if you want to introduce an exponent, no problem, because in the numerical solution, you can do that. It's very simple. It doesn't change much if you have to compute the outflow according to this equation or according to the same equation with the exponent of 0.5 here. Doesn't change much. You can do that. And also, you can, once that you gave up with the analytical integration, you can make this scheme more complicated. Why not introducing, for instance, here another discharge? So you may say, okay, when the storage reaches this level, then I start pouring from here a Q1, or let's say Q star T. This is fine. You just have to change your mass balance equation by putting a condition. The condition is that Q star is 0 until you get with the storage at a level, a fixed level. So let's identify this level as W star. And if W is lower than W star, then you don't have any outflow from here. If W reaches W star, you start with an outflow which could be linear and proportional to the exceedance of W with respect to W star, for instance. You may take whatever decision you want. And in fact, there is a class of models which are called tank models, or bucket, let me say bucket because it's more common. Bucket models, where a set of, let me call them complications, are introduced. Also, there are some models which assume that the storage has a maximum value. And when the maximum is reached, then all the rainfall is converted into river flow. There is no storage anymore. So you can decide a W max and you may impose that when W reaches W max, any further rainfall is automatically transformed in river flow without any additional storage. This is possible. There is one thing that you have to be careful about, which is, it seems simple to introduce additional discharges and to fix a maximum level for the storage, or you may introduce many other complications. But then be careful when you translate these complications into the mathematical equation, because it seems that they are so simple, but in practice, if you try to make an attempt, if I told you tomorrow, start from a linear reservoir, transform it in a non-linear one, and add mid-level discharge, you will see that the situation becomes more complicated than you would expect, with respect to what you would expect. And you have to be careful when translating in numerical solutions these conceptual schemes. And also, there is one other thing that you have to consider. When you introduce complications, this means additional parameters. And parameters, you know that, have to be calibrated. And if you have to calibrate just one parameter, we already said that it's easy. You can just adopt a trial and error procedure. But I said, even with two parameters, trial and error manual calibration becomes difficult. And then you have to use a numerical routine. And I said the numerical routine is fine. But I said it's fine even with the 6, 7 parameter. So when I said that, I implied that if you reach to a level of 10, 12, 15 parameters like some models have, it means that even the numerical routine, could take a lot of time and could be not so efficient. So you have to be careful when increasing the complexity of models, because simple models usually are more robust. What robust means is that maybe they are not really precise, but they don't make big mistakes. This is the definition of a robust model. If a model is reliable, we say that it's robust. A more precise model could be unrobust, which means more detailed, and it may happen that if parameters are estimated not correctly, then you get into big mistakes. So the number of parameters that you introduce should be commensurated to the information that you have available. If you have a lot of data to perform calibration and to check your model performances, then it's fine to use a complex model. If you don't have an extended information, it's better if you use a robust model. In this case, if I introduce a mid-level discharge, this is an additional parameter, because at least one. Because if I use a linear relationship, I have another linear coefficient here. And if I introduce a maximum level of storage, this is a parameter. W max is a parameter. How to select it? You have to estimate it. So increasing the complexity is always a bit problematic. Okay, but these bucket models are very popular, and there are many different types of these models. And there is one thing that we notice with this type of models, and one problem, one limitation, which is the threshold effect. Meaning that if you try to make an experiment in a computer and you introduce a mid-level discharge, you will see that the hydrograph may look like this. Q over time. You may have an hydrograph that starts from 0 if you don't have any initial flow, and then looks fine. But then when you get to the level of the mid-discharge, you may get a sudden change of slope in the hydrograph. And then you get to the maximum, and the same thing when you get in the recessing limb, you get a sudden change of slope when it's reached the level of the mid-discharge inside the tank. So we notice that these models, depending on the type of rainfall that you have, depending on how they are set up, may present a threshold problem. And therefore people started to think how to solve this. And basically, why there is this threshold problem? From a physical, practical point of view, why is that? The reason is simple, because the catchment is not like a tank. And in particular, the catchment is not like a tank with a mid-discharge. Because, you know, what does the mid-discharge mean from a practical point of view? What is the reason why you introduce that? The reason is that, you know, you realize that in your catchment, there is, at a certain point, you get into a situation where the catchment is saturated. It doesn't get any storage anymore, or if it's get more storage, it's very slow, the further accumulation of storage. And therefore, how to simulate this in a scheme like this? The only way is to introduce a mid-discharge. Because, of course, once that you get to this level, you obtain the fact that the storage is increasing much slower than before. So it's a good idea. The problem is that this situation of limited storage is not reached contemporarily over the whole catchment, like in this case. You have in the catchment some areas that start to get saturated, and then other ones are still receiving storing water. Other areas then get saturated, but still other ones, like, let me make a sketch. I don't remember. It was this one, the switch. Let me see. I don't risk anything today because, okay, it was this one. Good. So basically, let me suppose that this is a catchment with a river network. And typically what occurs when you get some rain over it, let's suppose that rain is uniformly distributed in space. When you get some rain over it, then you have part of you have at the beginning of the event the catchment that is storing water. But close to the river network, the catchment gets saturated very quickly. Why that? Because, so very close to the river network in these areas, after a relatively small time, you get saturation. Why is that? First of all, because close to the river, the catchment is very humid. And the second reason is that, of course, water flows down. And by flowing down, it saturates first the areas that are close to the river, while the upper areas are more likely to be not saturated. Of course, it also may happen, depending on the catchment, that in the upper areas you have rocks which get saturated very quickly. So it may be also that you get other areas that are saturated, which are not really close to the river network if you have rocks. But we see this predominant pattern of areas which are called I don't remember the term in English. It's okay, I will get it. Which are close to the river network, they get saturated. And then, if it continues raining, then this area is extended.